Hello friends, welcome to an interesting video in the series of electromagnetics and antennas. We'll discuss Maxwell's third equation today, so let us get straight into it. The Maxwell's third equation is derived from Faraday's law. That's the first thing that you need to remember, and I'll give a little prelude to what has happened so far. If we look at Maxwell's equations, for example, if we look at the Maxwell's first equation, which is the divergence equation, and says that divergence of D is equivalent to rho V, and further we have divergence of B is 0. The third equation is curl of E vector is minus curly B by curly T. Let me just write down these equations really quick. And curl of H is J plus curly D by curly T. Now if you look at these four equations closely, you'll find that these two equations are divergence equations and these two equations are curl equations. So diverging really signifies that something is moving out or something is moving into something which is static. So even if you look at the equations, you'll find the spatial change here. Del is a representative of curly by curly x plus curly by curly y and curly by curly z. So there is no time change here. So movement is not here in these two equations. But if you look at these two curl equations, you'll find that the things are changing with respect to time. So these are the dynamic equations and these are static equations. This is what is happening in the third equation. Something is changing with respect to time, which is causing some other thing to be produced. So that's the first thing that you need to remember. If we have a magnet here with the north and south pole and it is not moving, then of course we'll have the field lines going from north to south, and the divergence of those field lines eventually comes out to be 0 because the number of lines that come out of north pole are equal to the number of lines that go into the south pole. And if we look at the total flux in totality, that becomes 0. So if the same magnet is placed in, when water is being poured on this magnet and it causes this magnet to move, the flux lines will also change with respect to time in a particular space, and that change in the flux lines with respect to time will cause something else to be produced. And that is what Faraday says in his statement, that whenever magnetic flux, so this is the important thing, whenever the magnetic flux changes, it causes EMF to be produced. And of course, if we consider the right hand thumb rule here, the magnet is moving in the clockwise direction, so the EMF produced will have a positive side out of the board and the negative side inside the board. So in other words, it follows the right hand thumb rule, which is easy to understand. And if we place a conducting wire through it, and it'll conduct with some current flowing into it. The magnetic flux, if it was not changing with respect to time, it wasn't causing anything else to be produced. But when it started changing with respect to time, the magnetic flux, which happens only when the magnet moves, that will cause some EMF to be produced. So that was the background, that was the prelude I wanted to share. So let's get into the derivation part. It is derived from the Faraday's law and the Lenz's law. The Faraday's law was pretty simple, which states that the total magnetic flux, if it changes with respect to time, it will cause some EMF to be produced. And the Lenz's law says that there'll be a negative sign next to it because the EMF which is being produced will cause or will oppose the magnetic flux to change. So that's one thing that you need to remember, putting this negative sign because of the Lenz's law. And then we know that this magnetic flux, total magnetic flux, can be represented in terms of flux density. That has already been done in Maxwell's second equation. You could refer that. And so total magnetic flux represented in terms of magnetic flux density, a clever way of expression. And by the definition of EMF, the electromotive force, it is the closed line integral of the non-conservative electric field generated by a battery. So if we have a battery, the total electric field will be the total field in the entire closed loop. So E dot dl will be the total EMF. The total EMF produced by the battery will be the total EMF spent along the route in this closed loop. So that's the basic definition of EMF basically. So 1 and 2 will give me Maxwell's third equation. And this is Maxwell's third equation in integral form. You can see that E dot dl, which is obtained from the definition of EMF, is equivalent to minus of curly B by curly T into ds, and of course it's a surface integral with it that goes along with it. Now if we substitute this phi here and make a little rearrangement, and that rearrangement is that we take this d by dt inside the integral sign, and that becomes curly d by curly t. So that gives us Maxwell's third equation, which is derived from basically Faraday's law and the definition of EMF. As I mentioned time and again, that Maxwell was a very, very intelligent scientist who has helped us expressing the theorems in a more sophisticated mathematical expressions. And on applying the Stokes theorem on vector E, what we get is the Stokes theorem, by the way, relates a line integral to the surface integral, and it says that the Stokes theorem says that curl of any vector through the surface is equivalent to the line integral of that vector enclosing that surface. So I suggest you should look into the physical interpretation of Stokes theorem to understand this better, but simply put, you could remember this theorem as the relation between line and surface integral of any vector, any specific vector. For this case, we have taken up E on the left hand side and E on the right hand side. So if you look at star and double star, you get curl of E to be equivalent to minus curly B by curly T, and this is Maxwell's equation in differential form. We've gotten Maxwell's equation in integral form, third equation, and Maxwell's equation in differential form. So that is how you understand the Maxwell's third equation and derive this equation. And I hope this tutorial was of help. And if you liked the video, please give it a thumbs up and share this video among your friends. That will be a great help. And also, if you're not subscribed, click on that subscribe button right away, and don't forget to press that bell icon for latest updates. And I'll see you around in the next videos to come. You have a great day and a great life ahead. Bye bye.